Hello everyone, welcome to part 2 of step-by-step adding and subtracting 2D vectors using their components. Okay, so briefly I'll remind you that we have these 3 main steps that we're going to use to add and subtract vectors. And I'll also recommend these 2 videos that I've listed here on the bottom because there are some things that I went over in those videos that I won't spend extra time saying again in this video. Okay, so let's go ahead and start with our first example here. We have vector 1 and vector 2. And we are going to add these 2 vectors, okay? So let me remind you that the first step that we need to do is to find the magnitude of the x and y components of both vector 1 and vector 2. And from a previous video, we have this general equation to help us do that, okay? Where theta, remember, is the angle between the x-axis and our vector, okay? So we'll start off with vector 1. Vector 1's x component is going to have a magnitude equal to the magnitude of vector 1 multiplied by cosine theta. Okay, and remember, as I said, theta is the angle between the x-axis and the vector. So in this case, that would be 45 degrees. So it'll be 14 meters per second times cosine 45. And that'll give us 14 meters per second times the root 2 over 2, which is equal to 7 root 2 meters per second, okay? And let's go ahead and find the y component of vector 1. Now it's going to be sine of the angle, but when the angle is 45 degrees, sine of 45 is also root 2 over 2, so we're going to get something similar here. And we get 7 root 2 meters per second for the y component as well, okay? So we have those 2. For vector 2, okay, we're going to do the same thing. Let's find the magnitude of the x component first. So that'll be that times cosine theta. Remember, cosine theta is the angle between the x-axis and our vector. So in this case, okay, because we know this angle here from the positive x-axis is 240 degrees, and we know that from here to here is 180, then this angle here, which is the angle between the x-axis and our vector, is going to be 60 degrees, okay? So we're going to use 60 degrees here. So 10 meters per second times cosine 60. That's going to give us 10 times 1/2, which is 5 meters per second. And the y component, remember we're doing sine now, sine of the angle. So the y component of vector 2 is going to have a magnitude of 10 meters per second times sine 60, which is 10 times root 3 over 2. That'll give us 5 root 3 meters per second. There. Okay, so now we can move on to step 2, which is to add vector 1's x component and vector 2's x component to find the x component of the resultant vector, and to add vector 1's y component to vector 2's y component to find the y component of our resultant vector. And I've kind of drawn a visual up here where VT, T standing for total, is our resultant vector, okay? And so let's go ahead and do this real quick. Vector 1's x component, we know, is 7 root 2 meters per second. Oops, 7 root 2. And that's this right here. Okay. Now, vector 2's x component is 5 meters per second. And that is this vector right here. But you'll notice here that it actually points to the left, okay? And so now, because it's not just pointing in the positive direction, we have to consider direction, okay? And so here, although we're still adding vectors, we have to turn this into a negative 5 because it's pointing in the negative direction, okay? Likewise, for the y components, okay, vector 1's y component is 7 root 2 meters per second. And vector 2's y component is 5 root 3. However, it points down, okay? And so we're going to go ahead and make that negative as well. okay? So now what we really have is 7 root 2 minus 5, which is approximately 4.899 meters per second for the x component of our resultant vector. And for the y component of the resultant vector, it's 7 root 2 minus 5 root 3, which is approximately 1.239 meters per second. Okay. Now, because both the x and y component of our resultant vector is positive, we know that the resultant vector is going to be in the first quadrant. And that is shown here as well, where the resultant vector is indeed in the first quadrant. All right, so now let's move on to our last step, which is to find the magnitude and direction of the resultant vector. So we have the components of our resultant vector. So now all we have to do is find the magnitude of the resultant vector using this formula here, okay, which is derived from the Pythagorean theorem, okay, and I talk about that in one of my previous videos on understanding vector components. And so this will be that, which comes out to be 5.053 meters per second. And so that's the magnitude of our resultant vector, okay? Real quick, you can see here that I've written down approximations, so the rounded version of these calculations here. But really, when you're plugging it into your calculator, if possible, plug this in instead of what you find here rounded, because that will help you avoid a rounding error, okay? Now we're gonna find the direction of our resultant vector by doing the inverse tangent of the y component divided by the x component. Okay, those are commas, by the way. Okay, and so that would be the inverse tangent of 1.239 over 4.899, which is going to be 14.2 degrees, okay? And again, for the most accurate answer, you want to plug in the unrounded full versions here, but I'm just writing the rounded version to try and limit how much I have to write, okay? So yeah, we get 14.2, and that's going to be the angle above the x-axis here. So if I redrew this, it would look kind of like this, VT, and so this angle is 14.2 degrees, and the magnitude is 5.053 meters per second, okay? And so there's your magnitude, and there's the direction. Real quick, the reason why we do know that 14.2 degrees represents this angle here is because we've used the x and y component of our resultant vector, which is this here and that there. And so if we do the inverse tangent of the y component divided by the x component, we know that we're looking for that angle right there. Okay, so let's move on to our next example. And here, instead of doing v1 plus v2, so vector 1 plus vector 2, we're going to do vector 1 minus vector 2, okay? And so here, we're doing that. Okay, all right, so we can skip step 1 because it's going to be the exact same as our previous problem. We already have the x and y components of vector 1 and vector 2. Now the difference is in step 2, when we actually do the x components, instead of adding them, we're going to subtract, right? And so let's go ahead and do that really quickly. So here we should have vector 1's x component, which is 7 root 2 meters per second, minus vector 2's x component, but remember, it goes to the left, so we're going to have to make it negative. So it's minus negative 5 meters per second, okay? And here, for the y components, we have 7 root 2 meters per second for vector 1's y component, minus vector 2's y component, which again goes downward, so we're going to have to make this negative. So minus negative 5 root 3 meters per second. And in essence, what those two negative signs means is we're basically adding, right? And so we're going to go get 14.899 meters per second for the x component of the resultant vector, and disappear 18.56 meters per second for the y component. So now we have our two components of the resultant vector, and they're both positive, so we know that the resultant vector is going to be in the first quadrant, okay? And if I were to draw this out, we would have the x component of the resultant vector there, and the y component there. So our resultant vector would look something like this, okay? And this makes sense. This makes sense because vector 1, okay, is, let's do that in another color here. Vector 1 looks something like this. And then you have vector 2, which originally is pointing this way, okay? But because we're doing subtraction, we're doing minus vector 2, it's equivalent to us kind of flipping it around, right? And so when we do the tip-to-tail method, now we're moving this guy over. And so, you know, it's not to scale. I didn't draw everything exactly right, but we know that it should look something like that probably. And when the vectors are added, you get the resultant vector here in green, okay? All right, so now let's just find the magnitude and the direction of our resultant vector. So we can do that really quickly here by just doing what we know, which is the x component of the resultant vector squared plus the y component of the resultant vector squared, and taking the square root of that, which is 23.8 meters per second. And we can find the direction by doing the inverse tangent of the y component over the x component, which is this here. And that gives us an angle of 51.2 degrees, okay? And so what this tells us is that this green vector here, our resultant vector, has a magnitude of 23.8 meters per second and a direction of 51.2 degrees above the horizontal, okay? So real quick, let's just write our full answer, which is the resultant vector is 23.8 meters per second, 51.2 degrees above the horizontal. Okay, I do think I'm going to add a part 3 to this series because I want to do an example where the resultant vector ends up being in quadrant 3, and that would make expressing the direction, so the angle, just a little bit different, so we have to be careful of that.